We said that we can use transformers in many areas, and we would like to model the transformers. And if you watch another video that we would put on the study desk for you, you would see that you model things using 5 elements. These are current source, voltage source, resistor, inductor, and capacitor. So these are the elements that you use, and you use them appropriately. For instance, if you want to represent power loss, you can't use capacitance or inductance because they don't dissipate power. Only a resistance is associated with power dissipation, so you can use only resistance to dissipate power. So, okay, that's all right. And a picture of a representation of a transformer would be like this, and I'm talking here about a 2-winding transformer. So that would be the simplest of transformers. A 2-winding transformer is, in textbooks, would be represented like this. I know sometimes it's hard to see those colors, so I might stick to blue and black. So in a textbook, it might be represented this way. But you be careful here, because it doesn't mean that we construct the transformer like that. As I say, in a textbook, it's like this. In practice, it would be different. And I'll temporarily put one here, so you realize if you had a 2-winding transformer, it's more likely to be like this. So you would have a winding on here, where, of course, this represents many turns that go like this, and you would have another winding. I'll put that one in black. Another winding there. And you would have similar here. And another one there. So that's a 2-winding transformer, but as you can see, the primary and secondary are split. Instead of having primary, secondary, you would have half the primary here and half the primary here, and half the secondary and half the secondary. That's much better coupling between the two windings, much better magnetic coupling than the one that you would see there. And we'll talk about coupling a little bit later. So let's keep going. This here is represented as a rectangle, but it's really just a bunch of conductors that go round and round and round. Sometimes, in fact, quite often, you might find that this one here is actually split. So I'll redraw it split. Split like this. I was trying to save time, I think. So it's split like that into sections, which is a bit of a pain, but I'll do it. So you get a bit of a better representation of reality. So that's yeah. So they are in different sections, and similar here. And I will just put dots there. So I save a bit of time. Dot there. So same here as you have there. That is split. When you talk in practice, you tend to use the term LV and HV LV meaning low voltage side of the transformer, and HV meaning the high voltage side. Which one would you put next to the core? So this is the core. This is the core. One of those is LV, one of them is HV. Which one do you put on the core or close to the core? Remember, the core is earthed. So which one would you put next to the core? So normally you would put the LV next to the core, and the HV would be away from the core. Typically, the power transformers, they would have oil in them. So this whole thing will be in a tank, and that would sit in oil. What is the oil for? Yeah, cooling. Both answers are good. Cooling, because oil, of course, is a liquid, so it will naturally circulate, or you can force it and make it circulate. But it's also for insulation. So you can guess now why you have those gaps. You have those gaps so that the oil can circulate a bit more freely and cool the transformer. So LV next to the core, because the core is earthed, and you want minimum insulation between the core and this one, and LV would require less insulation. You get the advantage of the oil acting, of course, as an insulator between the HV and the LV. So typical construction would look like that. This is only a single phase, two-winding transformer. I don't want to draw the three-phase one, but the three-phase one typically would be we call it a three-leg core, one for A phase, one for B phase, and one for C phase. You do also have five-legged core, which sometimes called shell-type transformer. This means it's got three legs in the middle for the three phases, and then two legs without winding, which is there for a reason that I will mention afterwards. But typically, for economic reasons, your three-phase transformers would have only three legs, which is quite interesting, but we'll talk about that later. For now, we'll focus on single phase with primary side, secondary side, but remember, this is not a normal way to construct transformers. That's more normal, where the low voltage and high voltage side, they sit on the same leg so that you get maximum coupling, magnetic coupling between them. Now, when we analyze transformers, we are doing transformer modeling here. When you analyze transformers, with that, people probably forget why they analyze it the way they analyze it. But there is a fundamental principle that you are using. And you have to have that at the back of your mind all the time. Otherwise, things will not make sense at all. And the thing that you do is that you pretend that the practical transformer is equivalent to, so this symbol means is equivalent to a perfect transformer plus imperfections. So many times in life you think of something real, like even a person, your friend, is somebody perfect, but there may be some little things that may not be quite right. Right? So it's a fairly well used philosophy. Something practical is really something perfect. We do our best to make it as close to perfect as we can. However, there are some imperfections. usually small. If imperfections are small, then this idea is not a bad idea. And for transformers, especially power transformers, relatively, imperfections are quite small. Now, the reason we use that philosophy is that we know everything there is to know about a perfect transformer. And generally speaking, we know the losses. We know, sorry, the imperfections. We know the imperfections. We know we can model them reasonably easily. So the split then is quite natural. Okay, so let's talk about a perfect transformer. What do you know about a perfect transformer? There are indeed only two things to know about a perfect transformer. Not much. It's just two things. And what are those two things? Sorry? Zero losses, yeah. A consequence of zero losses would be something. But I'm probably after a couple of equations. So, yeah, so that the voltage ratio would be equal to the turns ratio. So that's one. And that comes out of this equation comes out of those assumptions. One of the assumptions is zero losses, but there are many other assumptions that you have to make to reach that. But intuitively, you've made all those assumptions, and when you've made all those assumptions, that equation comes out. If you want to derive this, I'm not deriving it for you, but if you want to derive it, what would you base your derivation on? If I say go and derive this, I could say now, derive this, please. You fail if you can't derive this. I could say that. So how would you derive this? Yeah. Perfect. That's Faraday's law, because Faraday's law says voltage in any circuit you pick. The magic of Faraday's law is that I can use anything. I can think of any circuit. I can say the circuit is around my head or in the air somewhere. So the voltage around any circuit is proportional to the flux linkage, which normally you use a symbol. I'll use that. Flux linkage. The rate of change of flux linking that circuit. Now, if there are many turns in the circuit, this lambda, it's actually flux linkage, which is n times the amount of flux linking the circuit. So you have, therefore, V equal to n d phi dt, where phi is the flux linking the circuit. The circuit happens to have n turns. And you could say that this is a situation here where you have n1 turns on that side and n2 turns on this side, and you got flux linking all of those. It's the same flux. If we make the assumption that there's no leakage, every bit of flux that links this one links the other one, so they see exactly the same flux. So you could say then that V1, the voltage across this one, I'll call it E1. I'll call it E1 for now. We'll talk about the difference between E1 and V1 later. So from there you get E1 equal to N1 d phi by dt, where the flux is there. That's a flux. And E2 is equal to N2 d phi by dt. And you can see from there you get E1 over E2. So therefore, E1 over E2 equal to N1 over N2. So this here is Faraday's law. What was his first name? he won't be very happy. You know, because of him, we are here. We'll have a job one day. We'll raise a family. We'll be able to go to the movies. We'll drive our electric car. We'll be able to visit our grandma because of him. So we have to remember his first name. What's his first name? Michael. Michael Faraday. So I say because of him, because our whole society works because of that equation. All the electricity you're generating, maybe you could argue the little bit that comes from photovoltaic generation doesn't use that, but most of our electricity that we generate, it comes from a generator that is based on that equation. Our motors, of course, you start, every time you start your car in the morning, you're relying on this because you got a motor, and the motor also relies on this. So this is a very important law for all of us, and it came from Michael Faraday, and you can see straight from that law you get your equation, you get your transformer equation. So we know the perfect transformer, it doesn't have any leakage. If it had some leakage, then you can't use this. Because if there was some leakage like that, that is, you got a certain amount of flux that links the primary side, but doesn't link the secondary side, then that would be different from this. So you can't do that division. It wouldn't be that easy. So that's why we have made an assumption there that there is no leakage. And that also is the reason why we build the transformer this way. When you build the transformer this way, rather than this way, you have less leakage because both of them are sitting together, so they are more intimately coupled. Therefore, they are less likely to suffer from leakage. All right. So that's one equation for the perfect transformer. And what is the other equation for the perfect transformer? You can get it many ways. The easiest way to get it is just to imagine a transformer and say to yourself that a transformer neither creates nor destroys energy. So the perfect transformer doesn't create, it doesn't destroy energy. Or power, for that matter. So what would happen then if you say, you know, the first time you see those equations, like when I was a kid and I first time see this equation, I'm very happy. I think, oh, you know, I can get this little thing and I'll put 10 volts in and I'll get 1,000 volts out. Very happy. And I'm thinking I'm creating something I can get money for. But your happiness, you quickly come back to earth when you realize that you might be stepping voltage, but what are you doing to current? You're stepping it down by the same amount. So you're not creating any power. So if you say P1 equal to P2, admitting that you're not creating any power, so you would say P1 equal to P2, whatever you put in is coming out. And the assumption there, of course, is that there's no losses, but also there's no creation of power. So if that's the case, then V1 I1 is equal to V2 I2. And therefore, you can say it many ways, but I'm not going to derive it. You can derive that yourself. So you'll get N I1 over I2 is actually equal to N2 over N1. It's just a reverse of that one. It has to be. Otherwise, you'll be creating power. And some people write this down as I1 N1 equal to I2 N2. And some people give it a name, and they call it ampere turn balance. Ampere turn balance, because this is ampere, this is turns, the product, they are balanced. That's for two-winding transformer. You can extend those equations to multi-winding transformer. in fact, if you do power electronics, you would see that I've done this in the power electronics book. And it's done in a mathematically elegant way, if I may say so. And have a look at it if you do power electronics. But for today, I will stick to just two windings. So that's E1 over E2 equal to N1 over N2, and I1 N1 equal to I2 N2. These are your two equations, and they come out of the following assumptions. One, we have assumed there is no leakage whatsoever. Two, we have assumed that whatever power we put in is coming out. I'll give you a little idea here and explore that. There are two ways of looking at P1 equal to P2. One way is look at it normally as people do in the power industry. They think of power as active power. They might be saying active power in is equal to active power out. The other way of looking at this is to say instantaneous power in is equal to instantaneous power out. And you can come up with slightly different conclusions dependent on which one you have used. Okay, so you can say active power in equal to active power out, or you can say instantaneous power in is equal to instantaneous power out. For the two conclusions to match, you would have to either say active power in equal to active power out and reactive power in equal to reactive power out. Then those two things would be equivalent to instantaneous power in equal to instantaneous power out. So roughly, I shouldn't use the word roughly here, really, I should say really, when you say instantaneous power in equals instantaneous power out, you are accounting for both active power and reactive power. If you stick to active power in equal to active power out, you are not saying anything about reactive power, so you might get slightly different conclusions. But if you wish me to talk about this again, I'm quite happy to talk about it. But for now, let's keep going. So this is the perfect transformer equation, this one here and that one there. And these are the only two things you need to know about the perfect transformer. You don't need to know anything else. You've said everything. We could actually go home now and say, we know everything about the perfect transformer. They are encapsulated in just those two equations. So you know everything about this. So let us see then what we can say about the imperfections. We'll look at them one by one. So I will rub this off now. And say that this is a perfect. This is a. We'll make this a real transformer. So we would. I can build things on this. So let's say this is perfect. So this is perfect. Let's say it's perfect. We are saying practical is equal to perfection plus imperfections. That's life. Practical is perfections plus imperfections. We've talked about perfection. Now let's talk about imperfections. At some point in life, you have to look at imperfections. So let's do that. What imperfections do you have in a transformer? Remember, when we talk about these things, it's always good to go back to those 5 elements that we talked about, because everything is going to be represented by them. The perfect voltage source, perfect current source, resistance, inductance, capacitance. So whatever you say, it's going to be, it has to relate directly to those. Sometimes it might be hard, like you might say, Tony is a perfect gentleman, plus some imperfections. And you might say, oh, one of the imperfections he has is he eats too much, right? Which is not far from the truth. So he eats too much. But it's quite hard to represent that imperfection by our elements, and we got 5 of them. You have to do a lot of thinking to represent that imperfection by any one of those 5 elements. Now, with your transformer, it's a bit easier. So think about the imperfections and think about how you're going to represent them. And you're restricted in the way you can represent them. You can only represent them by one of those 5 elements. And talking about those 5 elements, I have to say that there are 2 of them that you rarely use, but you still use them. That's a current source, a voltage source, and only if you have active devices. And the other 3, the resistance, capacitance, inductance, you use them all the time when you're looking at passive devices. And a transformer is a passive device. That means it will not have a current source in there or a voltage source in there. So it's a passive device. So it will be represented by those 3 things. So you cut down now to just 3 things: resistance, capacitance, and inductance. Okay, so perfect transformer. Got some imperfections. What are those imperfections? Copper losses. Okay, so copper loss is one, and the term loss means we are losing power or energy. So how are you going to represent the copper loss? You have 3 choices: resistance, inductance, capacitance. So which one has loss associated with it? Just resistance. So you're going to have resistance. And also what you realize, of course, it is copper loss. There are 2 types of losses. At this point in time, at this point in your career or your education, you have to think of things in a bit of an abstract way. You might say losses can be I squared R type losses if you're dealing with a system where the loss will depend on current, and you got V squared divided by R type losses where the loss depends more on the applied voltage rather than the current that's going through. So losses can depend on current going through, or it can depend on voltage you apply across, approximately. It's a good approximation, but it's still approximate. Okay, so copper loss, does it depend on the voltage I'm applying to the transformer, or does it depend on the current I'm pushing through the transformer? It depends on current. And because of that, you would see that the I squared R losses, that is a copper loss, is represented by resistance in series rather than parallel, because it's dependent on I rather than on V. And you, of course, have one on the other side. So this is R1 and R2. So these are your first imperfection. So that's the first imperfection. So imperfections are what we call copper loss. And that would be copper loss, so that would be represented by resistances R1 and R2. Note that we are calling them resistances. They actually don't exist as resistors. They are not resistors, they are resistances. There's a difference. A resistor is an actual device that you can touch and feel. A resistance is just a number. Like, I am not a resistor, but I have resistance. So I have a resistance. What would be my resistance from head to foot?
Well, everybody is different. Depends on your skin.
Yeah, it depends on your physiological condition. Like if you're sweating and you're not wearing anything, so from head to toe might be some number. But as engineers, especially as power engineers, it's good to have some feel of what it can be, especially in the worst case scenario. So, yeah.
1 kilo ohm?
Yeah, about 1 kilo ohm. Yeah, that would be not bad. And you know this because you know that 240 volts can kill, and you need somewhere tens of milliamps to kill. All right, so somebody could die with 50 milliamps. So if 240 volts can kill, then 1 kilo ohm, 240 volts gives you 24 milliamps. So that's getting in the range. So even can be half a kilo ohm, especially if you touch with this hand and that hand, you know. So from head to toe, it might be a bit higher. From this hand to that hand, it may be a bit smaller. And the problem there, of course, it goes through the heart region. So around about 1 kilo ohm is a good assumption. Can be a bit lower. Many times it is a bit higher. That's why a lot of people escape, because it so happens that the resistance, because they were dry and not good connections, they escaped. It was only 10 milliamps or 5. That's why they escaped. But it can happen that 240 volts pushes tens of milliamps into the body, depending on how good the contact is and how good the contact is on the floor as well, or whether it's hand to hand. So a kilo ohm is the kind of resistance a person would have now, or could have. The person has a resistance, but doesn't mean the person is a resistor. Of course, I'm not a resistor. You won't get much money selling me as a resistor, right? Okay, good. Copper loss. So we represent by resistances R1 and R2. Now, what other imperfections do you have for the transformer? Coil losses? Core losses, yes, core losses. And core loss is as a result of the flux that is in there. And what you have to picture in your mind is that this flux, it doesn't always go in that direction. In Australia and many other countries, of course, it would change direction 50 times a second. Not only it's changing direction, but it's also growing in quantity sinusoidally, nominally sinusoidally. It's growing in quantity of flux, going up and up and up, more and more and more flux, and then it goes less and less and less until there's no flux. You could draw the picture, of course. If you look at the amount of flux against time, it would be like this. So the amount, that is the number of lines, would be more and more and more. The core would be almost filled up with flux there, and then gets less and less and less, and then zero, and then the flux reverses and grows the other way, and it keeps going 50 times a second. Now, because of this, Faraday's law always applies. Faraday's law applies to any circuit that you can put on in this universe, and there are many circuits there. Some people might think, oh, I only see 2 circuits there. There's 1 and there is 2. Michael says, no, there are many circuits here, millions and billions of circuits. There's a circuit there. There's a circuit here. There's a circuit there. So there are circuits everywhere. Now, if you have a circuit and Faraday says there will be an EMF induced in that circuit if you have flux changing. Now, as long as the circuit is non-conductive or open, then nothing will happen. You will get an EMF, but you will not have any current flowing. Like if I take a magnet and go move that magnet around like this, just shake it like this, I am inducing voltages around many circuits, but nothing will happen because the circuits are not conductive, or they may be an open circuit. So Faraday is still right, but there's no current flowing. However, in this case, especially if I was naive, and sometimes I am naive. Naive, by the way, means stupid. It's just a nice way of saying stupid. If I was naive and I made this core of solid iron, then I have created a lot of circuits. Every circuit I draw within the solid iron is a conductive circuit. And if I change flux inside, or flux going through a conductive circuit, and I'm changing it, I will get an EMF according to Faraday's law. And because the circuit is conductive, the EMF will cause a current to flow. So if that core was solid, around those flux lines, you would have currents that we call eddy currents. And that would cause the core, in fact, to get hot and maybe even melt. So because of that, we have the so-called eddy current loss, which is a core loss. Of course, we prevent this by laminating the core. This means we break the path of the current by laminating. Laminations are sheets about fraction of a millimeter thickness, and they have insulation on them. So don't scratch laminations, because if you do, you will defeat the purpose of laminating. So they are laminated, which means that you break the path of the current, so very little eddy current would flow. If you want less eddy current, you would have thinner lamination, because within one thickness of the lamination, you still have little circles of eddy currents, little circuits of eddy currents. So we cut down the eddy current by laminating. The second loss that's prominent in iron is one that's a little bit harder to understand, but again, look at my notes that I wrote. I hope the examiners still keep those notes. I'm not teaching this anymore. In power electronics, I've got an explanation of the other iron loss, which is hysteresis loss. Hysteresis is essentially magnetizing the core as a permanent magnet and then destroying it 50 times a second. So you're creating a permanent magnet, permanent in inverted commas, and then destroying it 50 times a second. Now, if you do that, every time you create that magnet and then destroying it, you're losing a bit of power. As I say, I described that in detail in the power electronics book, so you can have a look at that. Now, those two losses, both of them are proportional to the flux, to the amount of flux, rather than to the amount of current that comes in. And the amount of flux is proportional to the voltage. So that's why the core loss is represented by a resistance that is in parallel, because it's proportional to E rather than to I that's going there. So normally called R naught, and normally put on the supply side, on the primary side of the transformer. You could technically put it on the other side as well. It shouldn't make any difference, but normally put on this side.
Just a question, Tony.
Yep.
What laminations for the big power transformers? How thick are they?
Quarter of a millimeter.
Still,
Yeah.
still small?
Yeah, still small. It wouldn't be more than, it would be of that fraction of a millimeter range, right? We got one in our lab, so you can go and have a look.
Big transformer?
Yeah, it's 11 kV. 11 kV to 415. It's a distribution transformer, so you can go and have a look, and you can see the lamination there. I would say somewhere between 0.25 and about 0.25 of a millimeter. Okay. Now, third imperfection. What other imperfections do you think the transformer would have? Leakage flux is definitely one. And in textbook, they might show our leakage flux here. And that's primary side leakage flux, and they might have a little bit there and call them secondary side leakage flux. They might say that. But this transformer is perfect, so I'm not going to draw leakage flux there. Okay. So the leakage flux what do you expect it to be proportional to? In order to answer that question, you have to know what flux is. And that's not an easy thing. But I would say to you something here that I hope at some point you realize. And this is what is really the beginning for us. We are electrical engineers. Where do we start our thinking? And there is an answer to that question, a fairly definite answer. And the answer is this. Our thinking as electrical engineers starts with two sentences. The first one is that charges exist. So charges exist, and there are two kinds, positive and negative. What happens after that, I'm not going into it, but that's the beginning. Just like everything, you know, even in religion, you have a beginning. I'm not quite sure what they are. I don't read too many religious books, but they will tell you how the world started. So that's the beginning, and you don't question anything before that. So us electrical engineers, we have a beginning, and the beginning for us is that charges exist. We don't care who made the charges. We don't care what color they are. We don't have to care about that. But we know that positive and negative charges exist. They got some properties, which I'm not going into at the moment, but that's the beginning. The other one, so the first sentence then is charges exist. The other one is flux exist. So we are not questioning why flux exist. They just exist. And flux exists whenever you have a current. So if a current flows, then there will be flux. We know the properties of flux. We don't know who created flux. We don't know why flux exists. Actually, we don't care why flux exists. So don't waste your... all of us have got limited computing and thinking capacity, all of us. So don't waste your thinking capacity, unless you want to be a physicist, of course. Then go ahead. But if you want to be an engineer, you don't worry about why flux exists. It's something that has been put there for us, and we use it. Just like charges has been put there for us, we use it. So, two sentences. Charges exist, and all material are made up of charges, positive and negative. And they got some properties, which are very easy properties. I'm not going into that. If you want to know, I've got some notes I can send you. And then the other one is flux exist, and you get flux whenever you have current. And what is current? We can easily answer that question because we know where we begin. We begin with charges. Current is just flow of charges. In fact, the rate of flow of charges. So we have everything we want. We have flux, and we have charges. And flux exists when there's a flow of charges. The flux, of course, they have properties. And the properties of the flux, it is encapsulated in 4 laws. Who came up with the 4 laws? Faraday's law is one of them. And there are 3 others. I won't go into that. You have to do fields and waves to understand that. But it's good to know that there are only 4 laws. And they haven't been challenged. They're still seen as correct. Einstein challenged Newton's laws, etc., and knows that Newton's laws are not quite right. But our 4 laws, they are okay. What's the name of those laws? Maxwell's. Yes, Maxwell's laws. So there are 4 of them. I won't go into what they are, but Faraday's law is one of those. So if you want to know all there is to know about flux and all there is to know about charges, just study those 4 laws, Maxwell's laws, and if you do fields and waves, you will be doing them. Okay. So flux exists. Now, we talk about the properties of flux, and Faraday's law is an example the property, an example of a property of flux. The other thing to say about flux is that, as I said before, whenever there is a current, there will be flux. If you want to have a bit of a picture of flux, you would do a simple experiment. Maybe you've done it before. You take a magnet, put it on a sheet of paper, put some iron filings, just shake it, and you would see the influence of flux. It has more influence near the pole, less influence away from the pole, and so on. We talk about an amount of flux, that is fine. We talk about flux density. And what I was coming to here is this idea of flux leads to what we call inductance. So there is leakage flux, and therefore leakage inductance. So we have to know what inductance is. We have to make sure we understand fully, 100%, what inductance is. You can't understand it 99%. You have to understand it 100%. 99% is not good enough. Otherwise, it's like your foundation. You know, you're going to get if you're going to buy, to get builders to build a house for you, and you're going to have, everything would be put onto that foundation for the house. You don't say, oh, 99% is right. You have to get the foundation 100% right. Then your thinking will be correct as you move away from that foundation. So you have to understand exactly what inductance means, because that's one of your 5 things that I told you about before. So you have to know what inductance means. Now, inductance relates directly back to flux. Directly. There's a direct relationship between inductance and flux. And flux is something that is a bit harder to understand, but we know that we just accept its existence. We can't say, where does flux come from? Why is it there? That's not our business. Flux always exists if there's a current. Now, what is inductance? So you've done electrical engineering for a little while now, and inductance really represents the foundation for you. And as I said, 100% understanding is needed here.
Well, inductance would be a resistance to a current change in the conductor. So then you go into your flux, I guess, and you probably say that.
You said inductance is a resistance. So already we are getting the language wrong. I said before, yeah. Yeah.
One of the properties, I guess.
Yeah. So I said, when I did that, I don't think it was your lecture, but I said, sometimes I'll make some grammatical errors, and I hope people forgive me for that. But with the language of engineering, we really have to get it 100% right. Although I do understand what you're trying to say, indeed, in order for us to differentiate, I agree with you that the inductance represents some kind of resistance. It's not a resistance. It's not, but some kind of resistance. And our predecessors, they knew about this, and they invented another word. So instead of saying resistance associated with inductance, there is some kind of resistance. They knew it was not resistance. So what did they do? They invented another word. What word did they invent? They invented the word reactance, so that they don't have to say resistance, because they knew resistance have got a very specific meaning. So they invented the word reactance. So yes, associated with inductance, there is a reactance, which means that it will control the flow of current. But it's certainly not resistance.
Well, I didn't mean it in that way, but yes. inductor as a component will resist, not as a resistance, but resist to change of current in the circuit. This is fundamental.
Yeah, yeah. But I can't use those words as a person who is teaching, because then I will set people on a wrong track. Yeah, I would say yes, it reacts to the to someone trying to get the current to go high. It has a reaction, and that reaction is called the reactance, and so on. But we'll get to that a bit later on. But certainly that's a property of it, but that doesn't tell me what inductance is. I need 100% understanding of what inductance is. That's a property. That's a property of the inductance. That's fine. It opposes the flow of current. It reacts to that flow of current. But what is its what's 100% correct answer? In other words, what is the definition of inductance? Now, what you will find is everything that we say will have some kind of characteristic that looks like this. Sometimes it will be voltage against current. So that's how you define the resistance. Now, if we want to define inductance, that's an L, by the way, there is a graph that defines it. So what's that graph? Here, there's a graph, and this R is the gradient. Now, it's a similar definition for inductance. And if you know that, you know what inductance is 100%. That's Faraday's law. That's not the definition of inductance. What is the definition of inductance? Okay. Let's put it this way. Let's compare you and I, right? So you push a current of 1 amp into me. Don't do that, but let's pretend. So you put one current inside me, and you get flux around me. I put 1 amp into you, you get twice the amount of flux for the same current. Who has higher inductance? The other person, right? So how do we define inductance then?
What's the amount of flux?
Yep. Yes.
Unit of current?
Exactly right. So the amount of flux for unit of current. Actually, it's the amount of flux linkage per unit of current. So L equal to N phi divided by I. So that's the definition of inductance. So something has more inductance if we get more flux when we put 1 amp into it. That's why a coil with many turns, you put 1 amp into it, you get a lot more flux than where you have 1 turn. If I have a piece of iron next to it, then I will push the inductance up because I need less current for the same amount of flux, and so on. So that's the definition of inductance. So the inductance is the gradient of this line. So L equal to gradient equal to N phi divided by I. Amount of flux linkage per ampere. Now, it is 10 o'clock, so I have to stop. I will continue next time. Thank you.